Welcome back to the Awesome Agents podcast. I'm Alex Rivera, and today we're talking about Google's Virgo Network, which is a lot.
It's a lot. And I think the headline numbers are actually underselling the interesting part here.
Okay, before you explain, help me set the scene. Why does the network inside a data center even matter for AI training?
So the classic problem is this. You have tens of thousands of GPUs doing a training run, and they all need to share gradients after every step. That communication is the bottleneck, not the compute. And the bigger your cluster, the worse it gets.
Right, because the network can't keep up with scale.
Exactly. There is even a name for it, the scaling tax. You double the cluster size, you don't get double the throughput. The gap grows with scale.
And that's what Virgo is trying to fix.
That's exactly what it is trying to fix. Google replaced the traditional spine and leaf topology with a flat two-layer architecture.
What does flat mean in practice here?
In a traditional fat tree network, traffic between nodes in different parts of the cluster has to go up through shared uplinks at the core. The more nodes you add, the more contention on those shared links per node effective bandwidth shrinks even as aggregate bandwidth grows.
So you spend more on hardware and get less efficient per chip.
Exactly. Virgo uses hieratic switches, which means more ports per switch, fewer hops per path, and less contention overall. What used to take 3 or 4 network tiers now fits in 2. Google calls it a collapsed fabric.
And the headline numbers are, what, 47 petabits per second?
47 petabits per second of non-blocking bisectional bandwidth, 134,000 TPU chips in a single data center, 4 by bandwidth per accelerator versus prior generation.
Those are big numbers. Is there a catch coming?
There's always a catch. First, the 47 petabits is accelerator to accelerator only. Storage I/O runs through a separate fabric called Jupyter with its own limits. You can't add those numbers together. They're 2 different networks for 2 different traffic patterns.
So Virgo handles a specific slice of traffic, not everything.
Right. Google splits the whole thing into 3 domains: scale up within a pod, scale out across pods, and Jupyter for storage and multi-site traffic.
Scale out being the truly new piece here?
That's the key innovation. It's a dedicated RDMA fabric designed for deterministic latency across pods, with no shared uplinks in the path.
And the latency improvement is 40% lower versus prior generation?
On unloaded latency, yes. In practice, that means multi-day training jobs are less likely to stall waiting on a single straggler node. They also ship sub-millisecond telemetry and automated hang detection, which anyone who has managed a large training run will appreciate.
Okay, they also mentioned NVIDIA support, which surprised me. These two don't always play nice.
That's the truly interesting part. Google and NVIDIA co-designed something called the Falcon Open Networking Protocol to connect Vera Rubin into Virgo. NVIDIA's normal preference is InfiniBand for high-performance GPU clusters. This is a standout departure from that.
Why would NVIDIA go along with it?
Because Google Cloud is one of the biggest customers they have. Meta signed a multi-billion-dollar workload deal to run on Google's AI hypercomputer earlier this year.
So NVIDIA plays by Google's rules when the contract is big enough.
Basically. And the result is you can fit 80,000 Vera Rubin NVL72 GPUs in a single data center connected to the same Virgo fabric as the TPUs.
So what are the real limitations here? Because I get the sense Google is being selective about what they shared.
A few things. The 134,000 chip number is Google's infrastructure ceiling. Individual customers won't be reserving anything close to that. There's also no published pricing that separates out networking costs, so you can't actually tell if this improves price performance for your specific workload.
What about independent benchmarks?
They don't exist yet. Google's 40% latency and near linear scaling claims are their own measurements against their own prior generation. And the comparison that would actually matter, Virgo-backed TPU 8T versus NVL72 on InfiniBand, hasn't been published. That will come from customers.
So we're trusting Google's self-reported numbers for now.
For now. The architecture description is detailed enough to reason about, which is more than most announcements give you. But the real world throughput on actual customer workloads is what matters, and we don't have that yet.
What's the one thing you'd tell someone trying to decide if this matters for their work?
The 4 by bandwidth per chip increase is the cleanest claim. If your training jobs are network bound, that headroom is real and should show up in runtimes. For the rest, wait for independent reports from early access customers before making infrastructure decisions.
Makes sense. Don't reorganize your budget around a Cloud Next announcement.
Not yet. Watch what people who actually get access report back.
Google Virgo Network, 47 petabits per second, 134,000 TPUs, and a lot of caveats worth watching. Thanks for breaking it down, Maya.
Happy to. There is a lot more under the hood than the press release admits.
I bet there is. Full write-up is at awesomeagents.ai, and we'll see you next time.